and then look specifically at optical isomerism. So optical isomerism is something that's specifically to A2 chemistry, but obviously we need to know all about isomerism, which we've done before in the past. We're going to have a quick recap of isomerism, what it is, the other couple of types, and then look in detail at optical isomerism. So isomerism, we're going to quick look at the different types, and we have then a few different types. So we have structural, stereo, geometrical, and optical. So the other three, structural, stereo, and geometrical, we've looked at before, and optical is going to be the new one. So when we're dealing with isomerism, if there's anything in here that you think, oh, I can't really remember this, something that's quite good then after looking at this and going through this to look back on would be these 3 points. So it'd be really useful if you're not really familiar with functional groups in organic chemistry, so things like carbonyl groups, alkynes, alkynes, alkenes, alkyls, carboxylic groups, any of our functional groups that we might add on in organic chemistry. If you can't really remember them, you can't remember how we would draw them, some good time after this session would be spent just sort of recapping that. To be honest, the best way to remember functional groups is just that really old-fashioned, write it down, look at it, learn it. So for functional groups, for drawing them out. So that's one thing. Knowing arrangement of bonds around carbon atoms. So when we're talking about 4 bonded carbons and how things look, if we're not really 100% sure how bonds are formed around carbon, that'd be something to have a quick look at again. And then what affects boiling points of organic molecules. So basically, it's a quick overview here of isomerism. Isomerism is basically split into 2 major groups. So we've got the structural isomerism over here, and then we have stereoisomerism bottom. So structural isomerism, this is where we've always got the same molecular formula. So the molecular formula doesn't change, but we have a different structural formula. So that's basically where they look different, but molecularly they are exactly the same. So the 3 types of structural isomerism we can have is chain isomerism. And so you can see from this image really quickly, it's just where a carbon has moved, the bond's moved and it's formed a chain rather than continuing. But molecularly that hasn't changed. We'll look at that in a bit more detail. We can have position isomerism. So we've got a functional group taking a different position in the molecule. Molecularly, it's still exactly the same, but structurally it's different. And then functional group isomerism, so that movement of that functional group into different places. So that is structural isomerism. So molecular formula is exactly the same, but structurally the formula is different. Stereoisomerism is where we have same molecular formula, but atoms occupy different positions in space. And this is quite different to this. So it's different. And the way it's different is because we have to remember that molecules are 3D. They're not actually these flat objects. So geometrical isomerism, this occurs due to restricted rotation of carbon-carbon double bonds. So basically when carbon and carbon bond together, because it can't rotate the same because we've got the double bonds, we have a restriction of rotation. So we can get 2 forms of isomerism, E and Z, also known as cis and trans. So we basically only get 2 different ways that can be formed in geometrical isomerism. And then optical, which we're going to look at today, which is when molecules have a chiral center. So don't worry too much about that because we'll look at that in a bit. So structural isomerism, like we said, we've got chain, positional, and functional. Our compounds have got the same molecular formula, but they have different structural formula. So here we go. This is quite a nice slide to come back to later. Just it gives you a really quick overview of the 3. So chain isomerism involves different arrangements along the carbon skeleton. They generally have similar chemical properties as each other, slightly different physical properties, And remember, the more branching we have, the lower boiling point we have. Positional, we always have the same carbon skeleton. We always have the same functional group, but the functional group is in different position. They all pretty much have similar chemical properties, slightly different physical properties. And finally, functional group. This is where we have a different functional group. Therefore, we're going to have different chemical properties and therefore different physical properties. We can have more than one type of isomerism occurring in the same molecule. And the more carbon atoms that we have present, the more potential isomers we can get. So we get more potential isomers being possible. So chain isomerism. So this is when we have different arrangements along the carbon skeleton. So we've got an example here. So we've got two structural isomers of C4H10 here. So we've got butane and 2-methyl propane. Molecularly, they're exactly the same, C4H10. Butane is a straight chain molecule. All our carbon atoms are in a single row. 2-methyl propane is a branch molecule. We've got 3 carbon atoms in a row and 1 carbon atom sticks out of the main chain. Major difference between that is 2-methyl propane is going to have a lower boiling point than butane. So that is an example of structural isomerism as a chain structural isomerism. So differences, looking at butane and 2-methyl propane again. Chemically, they have very similar properties because they have the same functional group present. Physically, things such as density and boiling point show trends according to the degree of branching. Again, the greater the branching, the lower the boiling point. So if this had even more branching, it was a different molecule, more branching, it would have an even lower boiling point. So straight chain isomers have higher values than branched ones, remember? So the greater the degree of branching, the lower the boiling point. Branching decreases the effectiveness of intermolecular forces. Therefore, less energy is required to separate those molecules. Back to basics here. Branched, lower boiling point, because the branching decreases those intermolecular forces, which means we need a little bit less energy to break those bonds. Second type of structural isomerism is that positional isomerism. So for example, this is where the molecule has the same functional group, but it's in a different position. So we're going to look at this one. We're going to look at alkenes. Alkenes have a double bond in them. There's always a double carbon-carbon double bond in an alkene. This alkene is pent-1ene, and we can obviously number it because we've got 1, 2, 3, 4, 5 carbons, so it's pent, but it's 1ene because that carbon-carbon double bond is on that first carbon to the second carbon. This one over here, we've got pent-2ene because that double bond is in this position instead. So the functional group is the same, but its position is changed. We don't have any other isomers with 5 carbons in their chain, but there are 3 other structural isomers with chain of 4 carbons. It's because obviously if we change the position of it, we can count it from either end. So actually if we put the bond here instead, it would then be pent-2ene again because we just count the carbons from this direction. Different example, position of a halogen in a haloalkane. So we've got 1 chlorobutane attached to first carbon, 2 chlorobutane. This is not 3 chlorobutane. And again, are we going to let me change that to a pen? Nope. Let's take that off. Let me show you why. Again, this is not 3 chlorobutane because we would start counting the carbons from this end. 2, 3, 4. So again, this one is exactly the same as that. It is 2 chlorobutane. So moving our chlorine along the chain makes new isomers. The position, remember, is measured from the end nearest to the functional group. Third example is 2 chlorobutane. It's not 3-chlorobutane. Okay, and there are 2 more structural isomers of C4H and ICl, but they have a longest chain of 3. They're just a few examples of our isomers there. So another example, position of our benzene positions, relative positions on a benzene ring. So we could have 1,2-dichlorobenzene, or 1,3-dichlorobenzene, or 1,4. So again, just another positional example. Again, and this time now we've got the example of, I'm just going to move that so we can actually see what we're talking about. And structural isomerism of functional groups. This time we've got the same molecular formula, but we've got different functional groups, which means they have different chemical properties and different physical properties. So alcohol and ethers, we can have aldehydes and ketones, acids and esters, but we'll look at that in a bit more detail now. So alcohols and ethers. So we could have ethanol, which is an alcohol, functional group ROH. Physical properties, that OH bond gives rise to hydrogen bonding. So we get a higher boiling point and solubility in water. It's a base, it's got a wide range of reactions. Or it could be swapped and it could be an ether, and we would have methoxymethane, which is an ether group, ROR, functional group. So there'd be no hydrogen bonding forming here, because obviously we don't have that OH hydrogen bond going on here. So there's a low boiling point, it's insoluble in water and it's inert. So the difference between them is huge because of that change of functional groups. Another example, aldehydes and ketones. Again, they have to pair up in these pairs. It can't be an alcohol and a ketone. It could be an alcohol or an ether, or an aldehyde and a ketone. Again, aldehydes, so we could have propanol or propanone. Aldehyde, ketone. Functional group for an aldehyde is obviously RCHO. Ketone is RCOR. So we've got our polar carbon double bond oxygen, and that gives our dipole-dipole interaction. It's easily oxidized to acids, same number of carbons, and it reduces primary alcohols. Whereas a ketone, we do have that polar bond again, which gives our dipole-dipole interaction. It undergoes oxidation under extreme conditions only, and that's due to the position of this bond, and it's able to reduce secondary alcohols. Finally, carboxylic acids and esters. So an example, we could have propanoic acid and methyl ethanoate. So our carboxylic acid, remember our functional group is RCOOH, esters RCOOR. So the OH bond gives rise again to hydrogen bonding. So we get that higher boiling point and solubility in water. It's acidic and reacts with alcohols. Whereas esters, there's no hydrogen bonding because we don't have that OH bond. Therefore, it's insoluble in water. It's actually fairly unreactive, and we can actually use it to hydrolyze things to acids. So it's very different properties chemically. So stereoisomerism. We're going to have a quick look at recap of the geometrical before we look at the main point of today, which is optical isomerism. So molecules that go through stereoisomerism have the same molecular formula, but they are joined to each other in different spatial arrangements, and that means they occupy a different position in 3-dimensional space. So geometrical isomerism, it's found in some, but not in all alkenes, and it occurs due to that restricted rotation of our carbon-carbon double bonds. So, and it comes in 2 forms, cis and trans. So, how to tell if geometrical isomerism exists in some alkenes? Here we go. So here we've got 2 different atoms, groups attached to each other. 2 different atoms, groups attached to each other. Yes. Geometrical isomerism. 2 similar atoms or groups attached to each other? No. You don't get geometrical isomerism. The reason for that is because it's obviously different on each side. So the positioning of them, it won't be different no matter which way the rotation happens. Whereas here we can have the rotation and they can swap around. Two similar atoms groups attached, again, because of this, it's not going to change it again. So once you get two similar atoms groups attached to one end of carbon-carbon double bond, you cannot have geometrical isomerism. So no matter which way we rotate this, it's going to be the same. So we can get it when we have two different groups of atoms attached. And again, we've got this one here, we've got two different atoms and groups attached. So therefore we can get geometrical isomerism. So we have cis ones. Groups of atoms are on the same side of the double bond. So these ones are the same, they're on the same side of the double bond, these ones are the same, those are the double bonds. Or trans groups are on opposite sides, which we can see really nicely there. So this happens because of the restricted rotation of carbon-carbon double bonds. Single covalent bonds can easily rotate. What happens, so what appears to be a different structure isn't. It can look like it is, but the way they're written out, they're the same. All these structures are the same because the carbon-carbon bonds have free rotation. So they don't have a carbon-carbon double bond. So they might look different, but they're actually the same because they have this free rotation. So as you can see here, this is freely rotating. It's actually just the same molecule. In carbon-carbon double bonds, we have restricted rotation. We don't have that rotation around the carbon bond. So the groups on either end of a bond are frozen in position. So it's not easy to flip between the two. So we've got that stickiness here. So it means that there's only two possibilities. The structures cannot interchange easily. So the atoms in the two molecules occupy different positions in space. So we either have cis or we have trans, and they cannot switch. They are one or the other. So cis are when non-hydrogen groups atoms are on the same side of the carbon-carbon bond. Trans are when non-hydrogen groups atoms are on the opposite side of the carbon-carbon double bond. For example, cis, they're on the same side. Trans on the opposite side. Cis, same side. Trans, opposite sides. Or we can use E and Z, so Zussmann and Entigen, which are German words. So Z is our higher priority groups. Atoms are on the same side. Entigen, our high priority groups, atoms are on opposite sides. So this would be cis, Z, and then the other would be E. So when we're talking about priority, we use a Kahn, Ingold, and Prelog convention. Okay, so greater priority is iodine, bromine, chlorine, fluorine, hydrogen. So, example, we would calculate the relative masses of the atoms groups attached to the carbon-carbon double bond here. So at the top, relative mass of this part would be 15. Relative mass of this section is 29, 1, because it's just got one little hydrogen, and then 15 down here. Work out the high priority group at either end. This is a high priority group on this side, high priority group on this side. So this is where we're going to draw a line, not across the middle, straight down there. Work out if the high priority groups are on the same side or different. So if they're on the same side, so we can draw a line here, it's Z, or if we're on the different side, it's E. So here it would be E. So if we drew the line here, our two high priority groups would be on opposite sides. Draw the line here, we're on the same side. That one's Z. Again, I'm going to try and draw these ones on myself. We've got the line here. There are two high priority groups on opposite sides. So we've got E, same side, Z. This time, these are high priority groups and on the same side, they're Z, opposite sides, E. Oops, let's clear all that. So there's only 3 structural isomers of C4H8 that are alkenes. Of these, only one exhibits geometrical isomerism, and that's actually butene. So butanene, we can't get geometrical isomerism. And the reason we can't is if we look here, we've only got one high priority group, so no matter where we put it, it would always be the same. 2-methyl propene, they're always on the same side, so actually it doesn't matter which way it rotates, they're always going to be the same. But butene, we can get cis and trans. So optical isomerism. Let's get something up. Basically, they're non-superimposable mirror images of each other. And I am on the wrong page here. Yes. So optical isomerism is when we have non-superimposable mirror images of a molecule, basically. It's basically like our left and right hands. They're mirror images of each other, but we cannot superimpose them onto each other. No matter what we do with them, they're not superimposable, because even though I do that, they're actually not the same on both sides. So they're like your left and right hand. They're a mirror image of each other, but they're not superimposable. We can't put them over each other. And that's what an optical isomer is. And an optical isomer will always have a chiral center. A chiral center is when we have 4 different groups bonded to one carbon atom. And we'll look at that in a bit more detail in a second. So, light waves. Let's just talk a little bit about planes of polarized light and light waves, because this is important in optical isomers as well. So light can be considered as a series of transverse waves. So if you think back to GCSE physics, and we've done lots with like slinkies, transverse waves oscillate at 90 degrees to the direction the light is moving. So we can model this by moving one end of the slinky up and down. So the direction of a wave is our propagation, and it oscillates 90 degrees to the direction of the light. So polarization. Polarization happens with transverse waves such as light. So this only happens during transverse waves. So what can happen is those transverse waves I just spoke about, they can vibrate in many planes that are 90 degrees to the direction of the wave propagation. So here we go, 90 degrees to it. And they can actually go through this at different angles. So let's just have a quick look at this. So these are all the different ways. There we go. So that is transverse waves. They can vibrate in many planes. There are 4 of the planes that we can vibrate in that are 90 degrees in the direction of the wave propagation. So for example, if we've got a light bulb, it produces waves in all the different possible planes at 90 degrees to the source. So like these 4 that we spoke about here, and this is our unpolarized light. So our light bulb produces all of those at all those different potential 90-degree angles, and this creates unpolarized light. In plane polarized light, all waves are in the same plane as each other. It's very similar to thinking about the edge of a piece of paper, and we can basically make an edge of a piece of paper here, here, or then basically anything in between. Okay, so all waves are in the same plane as each other. So we can't have all the different ones. So this can be achieved basically by shining unpolarized light through a polarizing filter, and the plane of polarized light is parallel to the filter. So basically what happens is, we've got the unpolarized light, we've got our filter, and as you can see, the only wave that then is going to pass through is the one that's in the same plane. The wave's only going to pass through is the one that is at that polarization is in that plane polarized light. So that is our plane polarized light, because that polarizing filter is at that right angle to that wave. Rotate it, and you'll notice a different plane of polarized light is going to pass through the polarizing filter. And every time you rotate it, a different plane of polarized light will pass through. If we added a second filter at right angles to the first, what you will find is no light gets through, because we've got the first one. We get that one wave passing through, but this polarizing filter is now in a different angle, 90 degrees angle, and that isn't the right plane for this wavelength to pass through. So this wave isn't going to pass through it. And so what you will get then is no light passing through. So we've got a plane polarized light, and then it gets stopped by the second filter. We have no light coming through. So optically active compounds. These are compounds that have the ability to rotate the plane of polarized light. So that's our polarized light, and we can rotate it. So they exist as two isomers, and we can also call these enantiomers. One is able to rotate the plane of polarized light clockwise, that is the plus or D isomer, and the other rotates the plane of polarized light anti-clockwise, and that is the minus or L enantiomer. So that's the two difference of them. So optical isomers rotate that plane of polarized light. That's the main gist of it, really. So when we talk about optical isomers, they're able to actually rotate the plane of polarized light. So what is an optical isomer then? I said an optical isomer is basically a molecule that is like this mirror image of each other that's non-superimposable. And they have to have this chiral carbon attached to it. So for a compound to be optically active, it must contain a carbon atom to which 4 different groups are added to it. So if we have a carbon like this, we call it a chiral carbon. And you will sometimes see a little asterisk next to it. And an asterisk next to a carbon denotes it as being a chiral carbon. So let's have a quick look here. So glycine isn't a chiral compound, but alanine has a chiral carbon. So the reason for this is glycine doesn't have 4 different groups attached to this carbon. So if we look at this carbon here, it's got hydrogen and hydrogen. So that's why it can't be chiral. If we looked at this carbon here, again, it hasn't got 4 different groups attached. It's only got 3 groups, so that carbon can't be a chiral carbon either. Whereas in alanine, we've got hydrogen, no other hydrogens attached, nitrogen, no other nitrogens. We've got our CH3 group attached, and then we've just got our carbon attached. So that is a chiral compound. So the amino acid glycine does not contain a chiral carbon, whereas alanine does. Alanine, therefore, is optically active, but glycine isn't. And remember, we mean it's optically active, it's able to rotate that plane of polarized light. So if we drew a chiral compound in its 3D form, it's possible to see how the 2 enantiomers are different. So here are optical isomers of alanine. So these are our, that's our 3D image of it. So here we go, alanine, we've got our chiral carbon here, hydrogen, NH2, COOH group, and our H3C group. And we're going to draw a mirror image of them. 2 enantiomers are mirror images of each other. So it doesn't matter how much we rotate them, we cannot superimpose them on top of each other. So would this compound be optically active? So we're looking for a chiral compound. So straight away, let's annotate this. We're looking for 4 groups coming off our carbon. Well, we've got 4 groups. Are the 4 groups different? Bromine, no other bromines. And CH3 group, yeah, that's fine. Oh, no, we've got hydrogen and hydrogen. So we would say no, oops. No, this is not optically active because it's not got a chiral carbon. Let's look at this one. Right, so we've got 2 potential carbons we can look at. Let's look at this one. This one's got, this one's got 4 different things coming off it. Let's have a look. So we've got chlorine, we've got bromine, we've got fluorine, we've got a carbon, that's fine. This one isn't the chiral carbon. I'll show you why, because it's got a carbon coming off a carbon and then 3 hydrogens, but we have got a chiral carbon here. So it would be optically active. Again, looking for the chiral carbon. So, okay, we've got lots of carbons with 4 things coming off them. Have we got any with 4 different things? No. So here we've got a hydrogen. No other hydrogens, got OH group, yeah. But then we've got a carbon and a carbon. So that one would not be optically active. Ignore that, that is wrong. That is a wrong answer on there. This one again, would it be optically active? Actually, let me go back a second. I don't know how to go back. One sec. I'm just going to draw underneath it. So I just realised I didn't count something properly on the other one. 1, 2, 3, 4, 5, yeah. Right, so I told you to ignore the answer to the other one. Bear with me, I didn't count properly. I thought it was only a 4 carbon compound. It's not a 4 carbon compound, it's a 5. So this one at the bottom is optically active, and I said it wasn't, and I apologise straight away now, hadn't counted my carbons. So we've got 1, 2, 3, 4, 5 carbons. This would be our potentially chiral carbon. Hydrogen attached to it, nothing else, yeah. Now, it's groups attached to it. So whilst we've got a carbon and carbon attached, this is a CH3 group attached. So if we sort them out to CH3, OH group, and then actually we could do this, group that off, so, and we can just then call that one a carbon. So actually that one was optically active. The difference between that one and this one is actually, well, let's look at this. That is the same. That is the same on both sides. So actually this one's going to be optically inactive because the OH group's in the middle. Depending on how we would rotate it, it would always be the same. So this one is going to be not optically active. Okay, clear all right. What would we predict this compound to be optically active? Let's have a look. So we've got carbon, we've got CH3 group coming off it, carbon and nitrogen coming off it, hydrogen, OH. So if we drew this out, it would look like this. Oops, just lost the screen. Just give me a second. Oops, what's happened? Lost the screen. Let's put that back. There we go. So yeah, that one would be optically active, and now I can't make screen full size, never mind. We'll get back to it in a minute, because we've got the 4 different groups around it. Why? Yeah, okay. What do we predict this compound to be optically active? We've got 4 different groups coming off that carbon, so yes, this one will be optically active. This one's not going to be optically active because we've got 2 chlorines coming off carbon. So it's not a chirocarbon. And then this one is going to be optically active because they're all four different. So we can measure optical isomerism, and we can use something called a polarimeter, so a polar meter, can be used to measure the optical activity of a solution. So what we do is we pass normal light through a plane polarizing or Polaroid filter. So we pass that light through exactly the same as before, and we'll get all those four different waves. That plane polarized light is then passed through a cuvette. And in that cuvette, we will have a solution. And in that solution is going to be have an optically active compound. So some type of molecule that's optically active. This will then cause a plane of polarization of the light to be rotated. That rotated light then will approach a second Polaroid, and the light is only able to pass through the second filter if it's in the plane of polarization, and that matches the plane of polarization of the filter. So the second filter is rotated until light is able to pass through, and the scale on the second Polaroid allows its degrees of rotation to be read off of it. So, properties of optical isomers, what is the point of them? So optical isomers have identical physical and chemical properties to each other. Really interestingly, it's their biological activity that's really different, and that's due to the shape of and specificity of biological receptors. So if we think back to biology, things like different receptors in the body, think about active sites, anything like that, because of everything in biology being very specific to shape, we change the shape of something, basically like our hands, they're mirror images of each other, they're non-superimposable, means they're going to biologically react differently in the body, but physically and chemically they're exactly the same. So one example is something called limonene. It's an optically active compound. The D isomer is found in the peel of citrus fruit and gives off an orange smell, whereas the L isomer is found in pine needles and cones, and it has that refreshing pine-like smell. So our smell receptors in our nose are actually able to distinguish between the two different isomers. Another example, I'm just going to add onto here, let me just go back a bit so I've got a bit more space, would be morphine. Notes, no, I didn't want notes on the pen. So morphine. So morphine is obviously a drug we give to people as a painkiller. One of the isomers is highly addictive. So one is addictive, but has poor pain relief. Whereas the other isomer is the opposite, is actually less addictive, but has better amounts of pain relief. Another example where they have different biological processes is LSD. LSD obviously is a hallucinogenic drug, but actually only one of the isomers is hallucinogenic. The other isomer isn't, and that's all to do with that optical isomerism. And another example is amino acids, but specifically the amino acid asparagine. So asparagine. This one is very similar to this limonene. One of the optical isomers has a bitter taste. The other has a sweet taste. This is how they vary quite a lot. So, optically active amino acids. So other than glycine, all alpha amino acids are all optically active because they all contain a chirocarbon. We've just spoken about chirocarbons. There are therefore two possible isomers of all the optically active amino acids. Usually only one type of optical isomer is produced by an organism. So in general, it's only the L isomers of amino acids that occur in nature. But there's something really interesting about that. So because they're the only ones that occur, we have the D isomers actually are found in bacterial cell walls of the amino acids. D isomers of amino acids are found in bacterial cell walls. And what's really good about this is we can use this to our advantage with antibiotics. Oops. So antibiotics make use of this because they target the bacterial cell walls. So basically they target the amino acids that have got the D isomer. So therefore they target bacterial cell walls and damage the bacterial amino acids and not the human proteins. So actually that's why our bodies don't get as ill from the antibiotics, and it does target the bacteria. So we've made use of that optical isomerism when producing medicine. So, so optically active compounds. No, synthesis of lactic acid. Now, when my computer stops doing something that I don't want it to do, here we go. So, nucleophilic attack on carbonyl compounds can lead to the formation of optical isomers. So, optical isomers can be naturally occurring, like the ones we just spoke about, but actually in lactic acid, we can have a nucleophilic attack on carbonyl compounds, and this can lead to the formation of optical isomers even. So, what happens is the geometry at the carbonyl carbon is trigonal planar. So this means that the carbon, the oxygen, and the hydrogen attached to it all lie in the same plane. They're all on the same plane, trigonal, because there's three of them tri. It is possible for a nucleophile, so a carbon-nitrogen ion, to come along and attack the carbonyl group from the left-hand side, remembering that we've got this dipole-dipole interaction, so we've got that negatively charged part and positively charged part. So the nucleophile comes along, we get this bonding here of carbon-carbon, we lose that carbon-oxygen bond, and then we have those two lone electrons there. As the nucleophile adds onto the carbonyl compound, carbon, the other groups are then repelled, because remember, it held that other shape because of the bonding and because of the charges. The charges have changed, so the other groups are now repelled from that side, and they result in the formation of a particular molecular shape. So we then get this shape being formed. If we treat it with hydrochloric acid, that replaces the nitrile group with a carboxyl group, and it forms lactic acid. However, we can actually do the nucleophile attack exactly the same, but from the right-hand side during the initial stage reaction. Same thing comes along, happens, nucleophile group comes along, it's going to attack from the right-hand side of the carbonyl group. So this time, the molecule, when the nucleophile adds onto the right-hand side, other groups are going to be repelled in the opposite direction. Therefore, we get a formation of a different molecular shape. Again, if we treat it with hydrochloric acid, it replaces the nitrile group with a carboxyl group, and we form lactic acid, but this time as a different optical isomer. As the chances of a nucleophile attacking from either side are equal, we have the two isomers are formed in equal amounts, and we call this, when we have equal amounts of the optical isomers, a racemic mixture. We call them racemates. They're a racemic mixture. And therefore, overall, it has no effect on the plane of polarized light because we've got equal quantities. So, optical isomers in drug manufacturing. Well, I've said to you before about how they're useful for antibiotics. If a drug is optically active, different N-timers may bind differently or not at all to target receptors in our body. So one might have a desired effect while the other may have no effect at all, or a different effect entirely. So like I was saying again about the morphine, one is highly addictive and doesn't give you any pain relief, whereas the other one doesn't have much addictiveness but gives you good pain relief. So we want one of them and not the other. It's really hard for us to separate them and actually just have the isomer that we really want, the most optimum isomer. So actually what we often use in drug manufacturing is a racemic mixture, because it's difficult and expensive to separate the two isomers, so we actually have them at equal quantities. So if they're at equal quantities, basically any of the bad stuff that we don't want is sort of balanced out by the good stuff. So for example, ibuprofen is optically active. Only the D isomer ibuprofen is pharmaceutically active, but the L ibuprofen is not harmful. So ibuprofen tablets contain a racemic mixture of the two enantiomers. And if one was harmful, we would then obviously have to separate them, but that's difficult and expensive. So if the other one isn't harmful and it doesn't really have any detrimental effects, we'll keep them there. Another example is the drug thalidomide. So the drug thalidomide, I'm really sure I can say that word, was used as a tranquilizer and a painkiller in the 1950s. It was sold as a wonder drug to reduce morning sickness, and it was prescribed to pregnant women. What ended up happening was around 10,000 children during the 50s and the 60s were born with deformities, lots of them being physical and limb deformities and limbs not being formed properly. This large number of babies with these severe birth defects was linked to the thalidomide use during pregnancy. And this is because thalidomide is a racemic drug. The D enantiomer is effective against morning sickness, but the L enantiomer is tetragenic and causes birth defects. Also, the D isomer is able to be converted to the L in the body. So we're not actually able to just make a pure mixture of just the D enantiomer, because in the body it's actually then converted to the L. So then those tetragenic effects would still happen. So we could spend all that money and time trying to separate them, and actually the other optical isomer would then be present in the body because our body resets it. So let's say we do want to separate some optical isomers. Let's say we've got something that's really worthwhile separating. So when optically active substances are made in the lab, the usual result is a racemic 50-50 mixture of the two. If one enantiomer is harmful or causes unpleasant side effects, the different optical isomers have to be separated. It's hard to achieve as they have identical chemical and physical properties. And separating optical isomers is therefore very time consuming and expensive, but can improve pharmacological activity. An example of this is Parkinson's disease. So Parkinson's disease, you have a chronic lack of dopamine in the brain, specifically in the motor regions of the brain. There was a drug form called L-DOPA. L, obviously the isomer for it, so the L and D. And what it's able to do is the L-DOPA was able to cross the blood-brain barrier and converted by enzymes, and it was able to be converted into dopamine in the brain. The D isomer didn't do this, so actually it's actually really worthwhile with the Parkinson's drug to actually separate two. So how do we get an optically pure compound? So optically pure compounds can be obtained from some racemic mixtures with biological methods. These natural pathways involve microorganisms and promote stereoselectivity. So for an example, lactic acid that we put in milk, we can make it in the lab, but in both cases, a race mixture is a result. So the D-lactic acid is found in muscle, but pure L-lactic acid does not occur naturally, and we have to obtain it from the racemic mixture. So we can do this with the mold penicillin, and this makes blue cheese. So given a racemic mixture, the mold feeds only on D-lactic acid, leaving pure L-lactic acid behind. So that's a naturally biological way we can separate them, which is really, really cool. So we can use cheese to actually, when we make the racemic mixture, get rid of the D-lactic acid and leave the L-lactic acid behind. Naturally, our bodies don't make the L, so we want to get rid of, make the D, so we want to get rid of the D. An alternative way is separation is actually, rather than making a racemic mixture, is just to actually synthesize just the optically pure product we want. That's better because we don't have to mess about doing separation. So for example, we could attach a group to the starting material, and that group could actually physically block one of the approaches the other reagent can make. So we can only make one N-tiomer. Another approach is to use naturally occurring chiral molecules. So for example, those L-amino acids or sugars as a starting point for synthesis. This technique is known as chiral pool synthesis, and it makes use of a pool of optically pure reactants to ensure there's only one type of optical isomer. And an alternative method is the use of a chiral catalyst. So chiral catalysts transfer their chirality to reactants so that only a single isomer is synthesized. So an example of a chiral catalyst includes using transition metal complexes prepared using chiral ligands, chiral organic compounds, and biological molecules such as enzymes. So again, the L-dopa that I was talking about earlier, William Knowles created one of the first chiral catalysts from a transition metal complex and used this technique to synthesize the L-dopa treatment for Parkinson's disease. So that's where the dopamine is able to be converted in the brain. So we will leave that there for today.